Craig Hogan, and welcome him to Toronto once again. And this is the second of two talks done in collaboration with Atomic, Molecular, and Optical. And that is a first for us, but hopefully not a last. I think it's a really good precedent to set, and we have much in common involving issues of quantum and interferometry. So the first speaker was Steve Meyer, who's here in the front row, a long-time cosmic microwave background person, but who has been seduced by Craig's ideas on holography to mount an experiment, and we heard the details of the mounting of that experiment yesterday. So Craig and I go back a very long way, and he was a graduate student of Martin Rees's back in the late 70s, into the, I guess, maybe 80s. Yeah. And then went on to Caltech, Chicago, and then took up a faculty position at University of Arizona, and moved from there to the University of Washington following the temperature differential. And then, rather recently, he's moved to Fermi Lab at the University of Chicago to take over as head of astrophysics at Fermi Lab, which is a good thing for Chicago. And this experiment is one of the outcomes. So, Craig and I, Craig is noted as a deep thinker. And so what we're going to hear today is deep thought from Craig on fundamental aspects of physics that have cosmological connections as well. Anyway, good.
Well, thank you. Thank you for that very dignified introduction. All right. Now for something completely different. Okay. Right. So I want to wind back to some foundations of physics and things that people were worried about in the early part of the last century. After they discovered relativity, they discovered quantum mechanics, and then they thought, whoops, they don't fit. Okay, so what was the problem? And first of all, I want to convince you it's still a problem. We have a patch for it. I mean, we've worked around it, but it's still a problem. So the basic problem is that classical geometry, so relativity, special and general relativity, is based on mathematical manifold. It's a smooth geometrical surface. It's made of definite points, based on this idea of locality. Everything that happens at a definite place and time. That's what events are. That's the primitive concept in Einstein's theory. And events are labeled by coordinates, and that's just a map out of the real numbers. This is not compatible with the mathematical character of quantum mechanics. So quantum physics, and by extension reality, because quantum physics is a theory of reality, they do not respect that. They do not respect locality. In quantum mechanics, nothing happens at a definite place or time. Instead of events happening at a different place labeled by coordinates, you have interactions. They're represented by operators on states. They don't happen at particular places in time, except in particular states when you might have a particular, still not definite. Still, nothing is actually ever definite. In a general state, the delocalization is actually macroscopic. It's not confined to microscopic scales. And we know this is true because it's proven in many experiments. So, I mean, you do many of them here. The Einstein-Podolsky-Rosen Bell inequality type experiments show that that's right. I'm not going to talk about that. I'm just going to take it as given. Now, the reason we've got used to this, and it hasn't been an emergency for the last 50 years, is that we have this theory called quantum field theory, which partially reconciles these two magisteria. And the way it does that is that it assumes that geometry just is classical. It is space-time as we're used to it. And it's, in GR, it's dynamical. Space-time moves in response to, matter tells space-time how to curve, as Wheeler said. But it's not a quantum system. It's still a definite manifold, definite solution of a classical equation. And it responds to matter, but it responds to what it thinks is classical matter, some kind of average not with no quantum properties of the matter. And then the quantum part of the theory is all in the matter. It's in the particles and the fields. And the way you do that is that you quantize field modes. And this is where the non-locality is dealt with, that you take a field mode like a plane wave or something. It doesn't have to be a plane wave, but something that extends spatially. And you quantize its amplitude. And so you just get around the problem that way, and it works great. It works fine for all the particle experiments, everything at Fermilab, all of that. And so in this setup, the space-time geometry is just assumed to be continuous and classical. It's just not part of the quantum system. But we know that can't be the whole story. Even though it's great for Fermilab, it's not the whole story. And so I have a kind of laundry list here. I'm going to go through some of them, but not all of them. I already mentioned the business about just the business of principle. Well, we have a workaround to that I just explained. But it is true that if there were quantum properties of the geometry, we've just assumed them away. So the fact that they don't appear in quantum field theory doesn't mean anything. It's a circular argument. We assume that they're not there. And then I'm going to go over some of these in more detail. The fact is that this splicing becomes inconsistent at the Planck scale. We know that geometry can't behave classically past the Planck scale. I'll come back to that. It's also true that field theory cannot predict the absolute gravitating energy of the physical vacuum. It's just an invented number. It's Einstein's cosmological constant from the point of view of general relativity and field theory. It doesn't have anything to say about it, but we know that the cosmic expansion is accelerating, so there is a number to explain. It's not zero. So something eventually has to be done about that. So it's called the dark energy problem. Now, there are these other theoretical hints. They're not observational hints, but they're theoretical hints that field theory is not the whole story. One of them is from gravitational theory. There are these strong hints that gravity and geometry, which are these things that we're describing as manifold, as a geometry, they're actually statistical behaviors of a system, presumably a quantum system. And the indications are things like the fact that general relativity can be derived thermodynamically. And if that's true, then the degrees of freedom of that system are not those of the metric. So there's new physics there that is not part of field theory, not part of GR. Another set of ideas comes out of black hole physics. And again, I'll come back to this in a minute. But basically that in the states of black holes appear to be thermodynamic systems, and they have their information encoded with a particular density, the Planck density, on two-dimensional surfaces, which is much less information than field theory has. So there's another indication that there's some non-locality going on in the gravitational system, whatever that is. So there are these reasons to think that physics needs to go beyond quantum field theory, even though QFT does great for particle physics. All right, so let me talk a bit about this scale, the Planck scale, because it's very important for all of these issues. Here's Max Planck. So in 1900, he wrote down nature's units of time, length. You can take his constant, the Planck constant, Newton's constant, and the speed of light, and you can derive from that a fundamental time or length, which is very, very small. The length is 10 to the minus 35 meters, which is way too small to observe directly. And this is the length that comes in because it's where gravity meets quantum. It's the length that comes in where quantum field theory becomes inconsistent. And this is an explanation of why. So you can plot the logarithm of the size of a system versus its mass. And you can put two curves on here. One of them is quantum stuff, Einstein's photoelectric relation. So the length goes like 1 over the energy. Higher energy things have a shorter wavelength. So this line corresponds to 1 quantum of energy. Quantum mechanics tells you can't have a system below that because that's less than 1 quantum. On the other side, you have gravity, and this is the Schwarzschild equation for the radius of a black hole of mass m, and it goes the other way. A more massive black hole is bigger. It's a larger Schwarzschild radius. And you can't have anything below this line in relativity because that's something that's more compact than a black hole, which is impossible. The two lines intersect at the Planck scale. And below that, everything is forbidden. So it's inconsistent. This idea of splicing together quantum and space-time just doesn't work anymore. Something has to give. The space-time has to be indeterminate or something. You have to change what you're doing. Of course, that's not necessarily a problem if you never reach the Planck scale. And in fact, it's fine in the applications of field theory. Let me talk a bit about this. So this is just a little bit of history on this other idea about gravity and how it appears to be a statistical behavior. So there's a long history of this going back to, 40 years now, back to the early 70s. So Bardeen et al. Showed that if you just look at the behavior of black holes, they obey equations which look like the laws of thermodynamics. For example, there's a thing like the second law. Entropy always increases. The area of an event horizon always increases, whatever black holes do. And that became more and more physically concrete. For example, when Bekenstein and Hawking analyzed the process of black hole evaporation, it showed that black holes actually behave like black bodies. They really are thermodynamic systems. Eventually, in the 90s, Jacobson showed that you could just derive the field equations thermodynamically from a statistical set of ideas, not using the equivalence principle. You can derive the equivalence principle from this. So it's an effective theory, like thermodynamics. It's some kind of average, where you don't know the fundamental degrees of freedom, but you know how many there are, how many degrees of freedom there are. And just a few years ago, Verlinde actually did the same thing, but also including just Newtonian gravity, with what he called an entropic formulation, which is a statistical formulation, which is just logically completely separate from space-time as a manifold. So if these ideas are right, they seem to be telling us something very deep about gravity.
Complete equivalence, the thermodynamic, because I mean, basically you can get tides out of the Newtonian gravity by thinking of not just temperature gradients, but gradients of temperature gradients.
Yeah.
That's fine, but what is a gravity wave in a thermodynamic formulation?
Yes. Well, it's very hard to describe in a thermodynamic formulation because that's not the right theory.
It's not clear that it's complete.
Well, they derive Einstein's equations, so they derive the same equations. So it's like the metaphor they use is it's like a gas. So the equation of sound, hydrodynamics and stuff like that, it's pretty hard to describe a sound wave in terms of the actual quantum constituents, which are molecules. The language you use is, pressure and,
The gravity waves are strain waves, so
Yeah.
maybe that's how it comes about. It's unclear.
No, I mean, the way they would do it is to go through GR. I mean, you derive GR from it. I mean, and these are...
Berlin didn't do that.
No, they didn't. Well, no, they just got to the field equations. Yeah. And but then we know that gravitational waves are a solution.
Jacobson showed it absolutely complete.
It was the same thing. He derived the field equations from...
Well, Berlin never went beyond Newtonian.
Yeah, he did. Yeah. At the end of the paper, he gets to GR, yeah. It doesn't really do more than Jacobson. It's wrapping Jacobson in different language. Yeah. Anyway, but, I mean, the standard line is that gravitons are the fundamental degrees of freedom, because that's what the spin 2 field... And these guys would say that's not right. The fundamental degrees of freedom are not the gravitons. And there are way fewer of them than there would be gravitons. Okay, so in fact, one example of that is the idea of holography. And it also grows out of black hole thermodynamics, because black holes have a two-dimensional boundary that encodes all the information of all of their states, we think, thermodynamically. Tuft and Susskind generalized that to say that it's not just black holes, but it's everything. And you can generalize that covariantly, as Busso showed. And there are concrete examples of this in ADS CFT space and string theory, sort of worked examples of holographic systems where a field theory on a boundary is dual, because mathematically equivalent, describes the same physics as a theory with gravity in the bulk. So again, this is another, there are sort of concrete examples of quantum states that have, where they're local in a boundary and non-local in the bulk. So locality depends upon which of the descriptions you're using. So it has led people to think about all of those ideas, lead to the idea that space-time could be an emergent system. It's not classical, it's a quantum system. And space-time and matter are just one quantum system, and space-time is an approximate behavior of this quantum system if you look at it over very long durations. And all these ideas that Einstein used, locality, that you derive in field theory separation of scales, they might only acquire meaning after many Planck times, on a macroscopic compared to the Planck scale, which is still could be very small. The Planck scale is so small. And if that's true, then the quantum matter and the geometry are entangled as one system. But it could be that there are new degrees of freedom belonging to the quantum geometry that you cannot describe using quantum fields or a quantized metric. They're just outside of that whole milieu. Another way of illustrating that is going back to this plot again. Physicists actually do have a theory to deal with this. String theory works down here. I mean, it's consistent because you can describe quantum states at those scales. But then the question is up here, could there be a quantum behavior of this regime, which is nearly classical, as we know, but could there be new quantum behaviors on large scales that we haven't described yet? There might be deviations from classical geometry on those scales, small enough to agree with experiments, but larger than the minimal deviations that you predict in field theory. I don't know whether this is useful, but I drew up this just to illustrate. So you can divide the world into classical and quantum and micro and macro. And usually we think of quantum things as being very small, things like atoms, particle interactions, stuff like that. But there are, of course, macroscopic quantum things as well. I mean, cavity modes, photon states are like that. Photon states coming into a telescope are big, the diameter of the primary aperture. EPR experiments, and maybe geometry is one of these. Maybe it's something where you could have quantum weirdness on a macroscopic scale. But it's worth thinking about. So here's a simple approach to this. As I've said, the quantum field theory assumes a classical space-time, and itself consistently, it predicts that Planck scale effects are very suppressed on large scales, so you don't have to worry about them. That's also true in string theory, but that's just because string theory uses field theory for its macroscopic limit. So it could be, and we wouldn't know about it from any of these ideas, that real geometry might have quantum effects on a larger scale. So what I want to do now is to talk about the consequences of a complementary approximation. Usually in quantum field theory, what you do is you take a classical geometry and you quantize the matter. But it's possible to flip that around and say, what happens if I take classical matter and I quantize the geometry? This is closer to what Verlinde does, because Verlinde talks about masses as if they're not quantum. They're just massive bodies, like when Einstein talks about positions of massive bodies. But let's see whether it's a consistent way to talk about that. Classical matter and quantum geometry. So the idea is that we could take what used to be coordinates and instead have quantum operators in place of the coordinates. But we're talking about the position of a massive body, so we're not going to try to talk about particles. We just forget about particle physics for the moment and talk about just quantum geometry. So we're not going to worry about any properties of a body aside from its position. And then we want a scale set by the Planck length. And we can also just ignore the quantum properties of light. We're talking about the phenomenology of this. But the positions of things, of anything, including mirrors, would be affected by the quantum geometry. So this is sort of, it's not a fundamental theory, but it's an effective theory of quantum geometry at large microscopic scales. Now, you can't just make up anything you want. There's a lot of constraints on it. So I guess I shouldn't spend too much time on this, but it has to be consistent quantum theory, which isn't trivial. It has to satisfy the Jacobi identities. It has to be consistent with classical geometry, so it has to have the right transformation properties that we're familiar with in the macroscopic limit. It has to be consistent with field theory, so you want to have things like plane wave modes that we're used to should propagate as if they were propagating in a classical space-time. And you'd like it to have a holographic density of state in order to get those other ideas into it. You'd like it to have the number of states to give you gravity from the thermodynamic derivations of GR. So you'd like the number of eigenstates in a volume to be equal to the surface area in Planck units. And it would be good if it were consistent with current experiments. So that's the challenge. And I'm going to describe several. I'm going to show you this is possible. You have a theory like this that does have new physics in it. So you could start off by writing down a covariant. So I just have I have a couple of technical slides. This is sort of before anyway, just as a preamble. The rest of the talk is not going to be like this, but I just want to do a little bit of this. So now, so this is a quantum commutator, and these are now, they're position operators, and they go 0, 1, 2, 3. There are 4 of them. Because when I take the classical limit, I want them to become normal classical positions. Now, why have I written down this equation? Well, I want a quantum equation, so there's a commutator. Because it's a commutator, it has to be antisymmetric in these indices. But since there are 4 of them, for them to be antisymmetric, I have to have a 4-component antisymmetric tensor on this side to make it covariant. But then I have 2 extra indices there, so I have to contract it with 2 vectors, things that transform as vectors. And the things that are available to me are the position and the 4 velocity. So if I do this, I can write down a covariant equation.
Who's 4 velocity?
The 4 velocity is the proper time derivative of the position. Okay, d by d tau of x.
So is it a quantum operator as well?
Yeah, in this one, it would have to be, yeah.
What's its commutator?
Well, we'll come back to that. Turns out you don't need to know for this, but anyway. And then you can either just express everything in Planck units or put a Planck thing there to get the dimensions right. So, say what? The body whose position you're describing. It's the proper time in its frame. So anyway, so the point I just made was that the form of that's dictated by covariance. And the thing that bothers people the most about this is that these states in this theory are not translation invariant. The commutator, the departure from classical behavior, depends on the position, which doesn't seem, well, it's not terrible because that, of course, is 0 for a classical theory, and it gets very small if this is very small, but it is something to worry about. A way to think about that is that the commutator does depend upon the world light of an observer. And this was already pointed out by Banks, that if you have an emergent space-time, it is emergent relative to a time-like trajectory. So that kind of makes sense. You can think about this as describing a quantum relationship between 2 time-like trajectories. So, the physical interpretation of this, it's a little bit hard, but it's a lot easier if you just transform to the rest frame of the body, which you're free to do. And then you have a 3-dimensional equation. It's a relationship between 2 trajectories. One of them, in that case, is the origin of the coordinate system, and the other is the body whose quantum state is being described. Okay? So
Okay, now I don't get that. So if we go back to, there is no U1 and U2, but you are describing, because you're doing 2 time-like trajectories, you're describing a U1 and U2, and that is an entering integer. Or it is one of, in other words, if it's 2 time-like trajectories, there are 2 U's. Where's the second one?
Well, the one of them is the rest frame of the coordinate system. I mean, this is covariant in any. I mean, there's a proper time, right? I mean, you can always define a proper time in any coordinate system. And this is the derivative in that coordinate system. And so if I transform to the rest frame of the body, then that equation becomes this equation. It goes away.
I get that, but
Yeah.
I don't see who, I mean, I like the idea of doing some kind of deviation, but
Yeah.
I don't see what you're deviating relative to some other rest frame of the coordinate system.
Well, it's a commutator, so it's the thing which is not. It's a deviation from classicality.
It's the equivalent statement as if I try and do something akin to general covariance and do transformations of the x's. How does that transform that commutator?
Yeah, so that's manifestly covariant, right? I mean, these are contracted with these. So it doesn't, you can transform to a different frame and the equation looks the same. But it's,
Okay, good, yes.
okay. But it's physically easier to think about in the rest frame, which is why I prefer this one. The first one is just there to show that it's a covariant origin. But this is more interesting to think about. You go to the rest frame of a body, which means that you're constraining the coordinate system to be moving at the same forward velocity, okay, whatever it is. But it doesn't have to be at the same place. It's moving at the same forward velocity. And then you get this equation. And what's interesting about this one is that you've seen it before. It's just the angular momentum algebra. It's really familiar, right? You know exactly how it behaves. You know all the solutions and everything. And so the idea is that this now, of course, it's angular momentum algebra, but instead of J, it has our positions X's here instead of J. So, which is unfamiliar. It's an unfamiliar application of that algebra. So, and so this would be, the states of this are like the states of an angular momentum of a body with a large angular momentum in the case of a body with a large physical separation. And the idea is that this describes quantum geometrical states of a massive body in its rest frame. So what are the consequences of that if you take it seriously? Well, so one thing you know from that algebra is that a body can't begin an eigenstate of position in more than one direction, just like angular momentum. So you have a discrete spectrum of states. And then you can count the number of states in the discrete spectrum. And so if you do that, the number of discrete states of a given definite radial separation, which is equivalent to total angular momentum, you can count them exactly, just like you do with angular momentum algebra. And if you have a three-sphere of radius r, which is like angular momentum of a certain total value, then the number of position eigenstates goes like r squared. It's like the number of spin states going like j squared. What's interesting about that is that's what you wanted. That's what we wanted. We wanted a holographic scaling for the number of states. And in fact, this agrees with the 4 pi that I just slipped in there. It agrees exactly with what Verlinde wants to get entropic gravity. So that fixes the normalization with no parameters if I want to get gravity out of it. So the claim is if these describe microstates of geometry, then gravity just pops out as entropically, according to Verlinde. But the really interesting thing, which is a new phenomenology, is that it also describes a new uncertainty in position that's much bigger than the Planck scale. So this is where it gets interesting. So just like with angular momentum, if you have a body of a certain angular momentum and you try to measure transverse component of angular momentum, there's uncertainty in it. And you can work that out here. And for the transverse components of position, the variance increases with the total separation, L. And you can put in units and work out that, say, on a laboratory scale, for L on the 1 meter scale, that variance in position is on the attometer scale. It's the geometric mean of the Planck length and the size of the apparatus, which is a measurable length. It's much bigger than the Planck length. So that's the estimated quantum departure from classical geometry. It's much bigger than the Planck scale, if that set of ideas is right. So the other interesting thing is that it's purely transverse. That is, there's no effect. The commutator vanishes because of the antisymmetric tensor. It vanishes if you only do measurements in one direction. It's only when you compare positions in different directions that you get any effect. So for that reason, it preserves the classicality of radial separation and the causal structure and the field theory modes that we worry about, that we care about. So the next question is, well, is that compatible with what we think? Yeah. Well, so in this equation, this is derived from that commutator with that in it. I just put that number in because I know that I wanted to get this exact number to agree with entropic gravity. Okay, so I could have put anything in but if I put that exact commutator coefficient in. In other words, it's like choosing the units of h bar for the theory. It's like putting in a 2 pi for h bar, because in this case it's the square root of 4 pi. Then I get, that's exactly what I want to get. Yeah. So that's, and that propagates through. That's why this number is what it is. Okay. So yeah.
This won't have escaped your notice, but so we've written down an algebra for x's, which are exactly like j's.
Yeah.
Since j's are the infinitesimal generators of a rotation group.
Yeah.
How do you interpret that in this space-time?
Yeah. So there's several interpretations. So you're talking about basically a representation of the group as.
Well, and
yeah.
And trying to actually
as spins.
have a
Yeah.
picture of what that would actually mean in
Yeah.
terms of space itself.
I think my personal visualization, I prefer to use waves, which is not the same as this, but it has the same amount of information in it. I mean, using the, even with angular momentum, visualizing it in terms of concrete representations of the rotation group, it's a little, yeah.
So that's kind of neat.
Yeah,
Sort of each
yeah,
little,
yeah.
so instead of an infinitesimal point, we're sort of thinking of
Yeah.
a point with extension, which has
Yeah,
sort of
that's right.
kind of rotational aspect to
That's
it.
right.
But that's just off the cuff without having thought about it.
Yeah.
And since one would say that with the angular
Yeah.
momentum, that the symmetry is the fundamental thing,
Yeah.
as opposed to the infinitesimal generator. Well, I mean, both fundamental, but there's a conjugate space, and there are angles associated with that conjugate
Yeah.
space. And
Yeah.
for those angles, it's like there's a conjugate phase space.
So it could very well be that that is the key to digging down into the source of this, because there is the angular wave numbers that translate into the distance, it's not part of this talk. Yeah, it's not part of this talk. Yeah, yeah.
It makes one think spin networks, but anyway.
Yeah, no, I mean, exactly. At least it could lead in a lot of different. Yes, that's true. No, it's an interesting. Yeah, but just in terms of the phenomenology, it agrees with what we know about space-time. So, for example, I gave you x perpendicular, so that translates into a delta theta as a function of scale, and that gets smaller on large scales. So the angles become more and more classical. The trajectories become more and more like rays as you go to large scales, which is what you want. You want it to emerge into a classical system. As you go to the Planck scale, the angles become indeterminate, and it becomes more and more holographic. You become aware that it's actually encoded in a two-dimensional system. So the classical limit is not the same as field theory. All right? The angles become less uncertain, but the transverse positions become more uncertain. And it has far fewer degrees of freedom than field theory does, especially on large scales. You really notice that. So another way to think about it is in terms of waves, which is why I put this here. But you can think about it this way. So if you're just talking about radial separation between world lines, these two world lines. This is Wigner's diagram, actually. You can measure the separation between events by bouncing light radially, and you could do that to high precision. But if you're talking about the transverse positions, the uncertainty is bigger, and it's just the diffraction limit. Basically, if you have basically the radial phase, if these are two wavefronts, is almost constant over a relatively large transverse patch, and that's where that length scale comes from. So you can either think about it in terms of like an angular momentum in the high J limit, or in terms of a bandwidth limited wave system. You get a similar description. So it's a way of saying that is that positions, relative positions, the information about positions are carried with this bandwidth limit, 1 over the Planck time. This is okay. It's the fidelity limit, and I think, and this is the point of view that Steve used yesterday, which is another nice way. So since he did it yesterday, I won't repeat it, but you can talk about, relative to some observer. Since it doesn't have, there's a world line here. you can define a causal diamond, which is the future of this point and the past of that point, which intersect in a surface. And the information about transverse location is encoded on these expanding wavefronts in the future and the past with that bandwidth limit. And when you get out to this distance, it has that diffractive uncertainty to it. So it's not a propagation effect on light. It's a diffraction effect on position information, on position wave functions, if you like. Okay. So if you think about it that way, I mean, of course, in quantum mechanics, so what I gave you an uncertainty principle, that's the width of a wave function. You never measure a wave function. You always measure, when you do a measurement, you don't measure wave function. What that corresponds to physically is a wave function here, which is a superposition of states. And in many measurements, you get selections from that wave function, which means that you have a noise. There's quantum uncertainty. And so this translates into fluctuations in transverse positions. If you measure two different directions, or transverse positions relative to a trajectory of that order, of that largish order. Now, I want to go back to the earlier question that I had, which was, how does it relate to standard quantum mechanics? And the answer is, it is complementary. That is, you can work out the standard quantum limit, just in standard quantum mechanics, for the uncertainty of position over some time interval, so in a causal diamond. And this is the answer. This is what you get for, say, standard quantum limit of an interferometer. And it turns out that that is much bigger than the geometrical uncertainty if the mass is much less than the Planck mass. So it's relatively simple, right? I mean, so standard quantum mechanics is the right theory to use if you're talking about quantum mechanics of things which are way much less than 10 to the minus 5 grams. Which, of course, particles are all, they're 10 to the minus 16 of the Planck mass, so it's a safe approximation, which is why field theory works great for elementary particles. But if you're talking about large masses, like mirrors and interferometers, you could have a Planckian uncertainty which is much larger than the standard quantum limit from geometrical quantum geometry effects. And it wouldn't have been noticed until now. This is what we're looking for. Now, there's another very strange aspect of this, which is the quantum weirdness that I haven't talked about. In order for locality to emerge in a sensible way, position states of nearby bodies have to be entangled with each other. They're not independent. If I measure the position of one body and another one, and they're both far away relative to me, but they're close to each other, they have to be in the same position state. They're not independent measurements. That's what it means to be a quantum geometry. That's why locality works. So, and it's consistent in this case because of the scaling of the fluctuations. This kind of illustrates how that works. The amplitude of the displacements is getting bigger as you go farther, even though the angle of the displacements gets bigger as you go smaller. Okay, so it's self-consistent to say that. If you could sort of imagine two bodies here relative to two bodies here, most of the excursions, which take place over long time scales corresponding to their macroscopic separations, that's in common. And there's small-scale fluctuations which happen faster. Okay? So this says this in different ways, that displacements of nearby bodies, they can't be independent for this to be consistent ways. This is how classical locality emerges. Things are entangled just by proximity, and the specific way that happens is that the events on null sheets, which are defined by some distant observer, they collapse into the same position state. That's what it means for the geometry to emerge, for it to become a classical thing. All right, so that concludes the theory part of my talk. And so how many of you came to Steve's talk yesterday? Okay, so I will now do an experimental talk, which is an abbreviated version of Steve's talk, which will be somewhat repetitious for the half of you that came to Steve's talk. Okay, so anyway, this is all to motivate an experiment, basically. Okay, and this is the experiment that we're doing at Fermilab. So most of the Fermilab experiments look like this, or something like that. You study particle tracks, which even though there's some quantum event in the middle, the tracks are classical things, and they don't have any quantum weirdness to them. The interferometers are sort of the other way around. This is looking at the optics of Geo 600. You have a massive body, and you're measuring macroscopic positions. This is of course, an old technology invented by Albert Michelson. Okay? And I guess you don't need to describe this in detail. The basic idea, right, is that you have massive bodies, in this case mirrors, and this is what Michelson called a half-silvered mirror, and we call a beam splitter. And by measuring the intensity of light here, you have a very precise measurement of the difference in the distance between these optics and these optics. So 2 directions over an extended volume is the key thing, with a very precise difference measurement. And in the old days, Michelson did it that way with his eyeball. And actually, the layout's quite similar to these days. That was his original apparatus. Modern machines use photodiodes instead of eyeballs, and use lasers instead of lamps. And so they're able to get to this atometer level of precision, a billionth of a meter. And non-locally with arm lengths, which are of order kilometers, up to kilometers. The other, how do they do that? I mean, sort of, this is much smaller than a wavelength of light, and the basic principle of it is that you can measure the phase very accurately if you have lots of photons. And so the motivation here is to have a laser with a lot of very high rate of photons, essentially in a condensed state of photons, and then you can measure position to a wavelength divided by the square root of the number of photons, which in our case is 10 to the 20, 10 to the 21 per second or so. So you really can get to atometer precision. So over short times, this is by far the best measurement technology. All right. So if you use in a differential sense, if you, the language of atomic clocks or Allen variance, you can talk about delta nu over nu or delta t over tau, and that variance is given by, well, now reaches Planckian, the square root of the Planck time, for times of order seconds. That delta nu over nu is less than 10 to the minus 20. Right, so it's about 7 orders of magnitude better than the best atomic clocks. This is just to show why this is the way to do the experiment, right? There's the right technology, that you could compare the fluctuation in meters, the log of the fluctuation in meters versus a length of time interval, which is the size of the causal diamond. These are all the precision experiments, technologies that are sitting around for measuring position, and the gap here is 10 to the minus 20. This is the Planckian quantum geometrical noise prediction, and the interferometers are there. They're down in the region where you can see the effect, if there is one. All right, so what happens in a Michelson interferometer? The space-time diagram of this is that you have a trajectory of the beam splitter and 2 end mirrors. And when you measure the signal, you're measuring a phase which depends upon the positions of things at these 4 events at any given time. So it's a non-local experiment. The light comes in and goes off to the 2 arms and comes back again. And if you look up close at the beam splitter, the way to think about it is that a wavefront comes in, hits the beam splitter and reflects off and transmits half, and then it comes back a microsecond later, but by that time it's in a different position. It's in a different place. It's a different part of the causal diamond. The geometrical noise is kicked in, and it's actually moved by about this amount. So there's a fluctuation. And you can work out what the spectral density of the phase noise is, basically from those considerations, so including the transfer function, which is the thing that you're measuring is the comparison of the phases. You have this formula for the noise spectrum, which has no parameters in it. You know what the numbers are. It only depends upon the length of the system and the Planck time and nothing else. So you have a very definite target for what you think the noise should be. That's what it is. And I can even play it for you. Did you do that? So you can slow it down by a factor of 10,000. It's just filtered noise. It's not exactly white. It sounds like that. Video. Okay, so then the question is, does that agree with what we know already? How does it compare with current experiments? And that's shown here. So that noise plot for different experiments has these envelopes. This is for 4-kilometer arms, 600-meter arms, and 40-meter arms. And the measured noise in the existing interferometers is shown by these dots. Now, there's a subtlety with LIGO in that this would be the prediction for LIGO. And for gravitational waves, LIGO is down here. But for the geometrical noise effect, it's not as sensitive, and that's because of the layout of the interferometer. I guess I won't go into the details unless people want to talk about that. What's actually more sensitive now, the most constraining experiment is GEO600, which is actually only about a factor of 2 from detecting this already. And then the Fermilab experiment is projected to have enough sensitivity to easily detect the effect if it's there. So GEO600, because of its design, I guess, yeah, it's about a factor of 2. This is the predicted level of noise. This is in strain units. And that's the last published measured noise curve that I could find. So it's from like a year or two ago. So they're close. It's not, and this wasn't even designed to do this. This was designed to look for gravitational waves. So at Fermilab, we're building a machine to look for this effect. Okay, and this is what Steve talked about yesterday. Did you explain where we got the name? Okay, so this is new. So holometer, of course, is short for holographic interferometer. Also, it's a word. So in the Oxford English Dictionary, you can look up holometer, and it's an ancient word from the 17th century. It means a mathematical instrument for making all kinds of measurements. So that's what we're building. That's why we didn't choose an acronym, because there's a perfect name for it. Okay, and then the basic principle is that we're designing this. It's not for gravitational waves. It's for looking for quantum geometrical noise. And it's designed to get a positive signal if it's there, and to distinguish it from other noise, so we don't get a false positive. So we can rule it out. And particularly to get, in the end, sub-Planckian sensitivity, because for some reason my experimental colleagues don't believe my exact factor of the square root of 4 pi, only because I've changed my mind 5 or 6 times about the number. They don't believe me anymore. Although, I mean, I don't know. I'm going to stop worrying about it. They're going to build an experiment which is sub-Planckian in sensitivity. And we'll have signatures. So that the frequency spectrum I showed you and the equivalent in the time domain have a particular shape that should not be reproduced by just random sources of noise. So, and a particular amplitude as well, which we expect, Planckian amplitude. So the basic concept is that we have 2 Michelson interferometers. They're power recycled to have lots of power at the beam splitters to reduce the photon shock noise. But the main idea is that you have 2 interferometers, they're next to each other, and you correlate their outputs. So if you draw a space-time diagram, these are the arms of the interferometers at one time, so the world line of the beam splitters. So they probe the same volume of space-time. And so because of the entanglement and the coherence, the signals should be correlated, if that's the way space-time emerges. If emergent space-time happens the way that I described, they should have an in common Planckian noise from that. Right, this is just another cartoon statement of the same thing. 2 interferometers next to each other, each of them a power recycled Michelson. All right, so I won't go into any of that unless you want to talk about it again. And again, this is the main point, that you get a correlated signal if the spacetimes overlap, but if you reconfigure the system, for example, back-to-back, or one of them in a straight line, different ways to do that, then you turn off the in common space-time correlation. Viewed from the top, that they overlap if they're next to each other, and these two do not overlap. The position information is propagating independently in a different configuration. So the machine actually has mostly been built. This is from over a year ago now, and so it's actually more advanced than this. But this, just to show you the scale of the thing. So these are the two vacuum vessels. They're about this big, each of them where the beam splitters are. And this is looking down. And so these are the beginnings of two 40-meter arms, and there's two others that are going to go in here. Well, they're there now. And this is where it is. If you know the Fermilab site, this is the Tevatron, which is exactly 1 kilometer in radius. There's Wilson Hall. If you go out the fixed beam, fixed target line out here in the Maison area and blow it up, we have two interferometers arm underneath an earth berm in this tunnel, which was just an existing tunnel that we found. And there's actually another tunnel that keeps going that way that we can use. And the two other arms go out to the side here. And these were just built in literally a green field. And this is just a trailer, okay, cars for scale. That's inside the tunnel. That's what it looks, well, that's what it looked like too before we moved in. And this is outside, laying down the vacuum system and the insulation for baking, and inside where the laser tables are set up. So that's pretty much what it looks like now to scale, human, under construction. I had to show this. You didn't show this, right? Yeah. So Michelson, at the end of his career, did the first large-scale vacuum interferometer experiment. Unlike Michelson-Morley, which was done on a tabletop, he used water pipes and pumped the air out to get phase stability. And this was a system that he built near where Midway Airport is now. And it was about 1,000 by 2,000 feet, and he was able to measure the rotation of the Earth from this. It's a Mach-Zehnder configuration. Anyway, I like this because it kind of looks like our experiment. Got, sheds and pipes. There's our shed. This is Lee McCullough putting together the end station. That's what it looks like inside. This shows you the scale. It's like LIGO, but it's miniature. So this is the end station of LIGO. In LIGO, this is a gigantic tower of seismic isolation machinery. And here, I guess this is Steve's advanced seismic isolation technology, which is with two metal plates sitting on rubber balls. Did I describe that accurately? Yeah, Viton balls, special rubber. And this is the beam splitter and the power recycling mirror. It's a rather simple system, a pretty standard laser table. All right, so I just wanted to comment a little bit about the controversy here. So it's driven theorists nuts that we even related to the holographic principle at all. Lenny Susskind was called by a reporter, and he said, the idea that this tests anything of interest is silly, before refusing to elaborate and abruptly hanging up the phone. And in fact, Busso and Susskind wrote a letter where they said this. So, I mean, they're skeptical about this. So I want to just say my opinion about the situation. So the claim is, they say, that the holographic principle does not predict the quantum jitters that Hogan's experiment seeks to detect. It predicts their absence. They would conflict with Einstein's principle of relativity, blah, blah, blah. We believe that Hogan's experiment does not actually test this principle. So I want to point out a couple of things. One is that up here, they say, it predicts their absence, and then it says it does not actually test, which I think just doesn't make sense. If it makes a prediction, then we're testing it. Never mind that. I actually agree with them. I actually agree that the experiment does not test the holographic principle. It tests a particular set of ideas for how emergent space-time could work with holographic information densities. It doesn't test the holographic principle. And it's true that it violates general relativity, but that's because general relativity is a classical theory, and this is looking for a quantum effect. It's designed not to see classical effects. I claim that it's consistent with previous experiments, but they kind of hint that it's not, but I think it is. And it's consistent with their holographic bounds, and with relativity as a classical limit. That's what I think. So we just have different attitudes about it. I actually agree with most of what they say, although it doesn't make a lot amount of sense. It's not true that we're testing quantum gravity. It's not foam-like. There's no quantum foam in this theory. That's another journalistic frivolity. Okay. So just to be clear about that. So this is the team, and it's being led by real experimentalists, Steve and Aaron. It's mostly funded by Aaron's early career award, which has made the construction possible. And it's also enabled by, again, on a continuing basis, by people from LIGO. So particularly Ray Weiss and Sam Waldman have been critical to making this work, and especially making it happen quickly without big mistakes along the way. The status is that it's currently under commissioning. There are these 2 power recycled 40-meter interferometers working, and the system's being tuned up to operate at Planck sensitivity. I think it's going to take a year or 2 to get there, but who knows? It's moving pretty fast. And so finally, let's just say, what are the outcomes? If we don't see the noise, what does it mean? Well, it's a kind of a mouthful, right? We're setting a subplankian upper limit on this parameter of the non-computed geometry in that spiel that I gave you, or position information encoding bandwidth in that implementation. So that's not going to set the world on edge, okay? It does mean that the information density of the positions of the mirrors would exceed the holographic bound, whatever that means. If we see it, then we are probing something about Planckian quantum geometry, which would be very exciting. And would mean that the information density of the position states is about equal to the holographic bound, as I showed you. All right, so I just have one more slide, because I'm pretty sure that Steve didn't show this, which is the video that Jennifer, you didn't do this, did you? Okay, so you can get this on YouTube. And so this was made in the tunnel at an earlier stage of the experiment, before the advanced seismic isolation with the rubber feet was in, when Steve was trying to diagnose how environmental noise was getting into the system. So the idea is you hook up the output of the interferometer to speakers and just listen to it when you bang on it. And so this is what this is Steve doing his sophisticated probe. That's what it sounds like. That's the interferometer response that you're hearing. Doesn't sound like this anymore. Anyway, I just think that's classic. Okay, I'll stop there. Thank you. Yeah, I think, but I mean, I think it would find that difficult anyway. That is, because the number of different positions is.
If I put 15 different beam splitters in
Yeah.
the center of your apparatus,
Yeah.
would it be impossible for them all to actually have the same position in the sense that you rely on them for measurement?
So the positions are always defined relative to an observer's, in this case, something far away. The closer you get, the more holographic it gets. And yeah, the number of position states is limited, right? So in a sense, the noise that we're seeing as a result is because of that. It's because of that limit on the number of position states. Yeah.
Understand the equal picture of the non-commutative geometric picture, which is based on conditionalization. Is there an equivalent Schrödinger equation one can actually write down for these things and what space would the observer live in?
Yeah, Schrödinger equation. So, no is the answer, not yet. I mean, so it's like saying, is there a Schrödinger equation for angular momentum? And the answer is not really, not on its own. You need to supplement it with more, more theoretical dynamics. This is as if you only had angular momentum algebra and nothing else, no other physics in it.
Just a non-expert question. At the very beginning, you had, when you were describing the Planck scale, combination of constants. How does that combination of constants come about? It's not just saying, hey, how can we combine this to give us units of meters? There's presumably some derivation of that or something.
Well, so what Planck noticed was that, once he invented the idea of a quantum of action to get blackbody radiation right. Once you had that, there's just a unique combination of that with all the other constants of nature that you can put together natural units, as he called them, for length, time, and mass. And so it doesn't determine factors of 2 pi and things like that. But to within factors of order unity, that's all you need to know. There's nothing else in it.
I have a question. So the commutator relation, if I add x prime,
You can put it.
What happens?
You can put in an x dot, and you can do that consistently. X dot, right? X d by dt.
You could do that. That wasn't what I was referring to.
You want x d by dx.
Deal
Dx mu by d mu.
translations of this.
Yeah. Yeah, I don't know how to do that. Yeah.
And it doesn't seem, it's not invariant under that.
Right. No, I mean.
The x, and so,
Yeah.
then one might wonder whether the x's, I was fooling around with this, didn't get anywhere, but.
Yeah. It still works radially.
Whether one could think of x as sort of an x minus x equilibrium, that it's.
Yeah.
I mean, I'm trying to do the jiggle aspect of this. You're telling me always that I'm not right, but in fact, it's, there are many intriguing aspects because really what one's talking about is when you're dealing with a point, you're probably dealing with the limit. Because if you fuzz out a point, then you're probing a larger region of space-time. And as you, let me just fool around with this and see what you think. So BKL of if you go down towards the singularity, then it's unstable to arbitrary anisotropy. This is what's called the mixed master universe.
Yeah, I do remember that. Yes.
And so what happens there is that as you propagate down towards the origin, it's the time translations which are the fundamental thing, and you sort of have a shear tensor, strain tensor, which is moving around in all possible ways. And so it's sort of a statistical probing of all possible orientation of this. And so in that sense, at some level, I was wondering whether this relationship to a rotation group and a effective symmetry is developing, whether that could be a statistical thing associated with that process, but that's trying to look at a space-time point as an extended thing and then approach the limit of it going down towards zero, which may or may not have relevance to this. Maybe. No, but I mean,
Yeah.
see, that's what happens when you're dealing with emergence.
Yeah.
You turn it around.
Yeah.
And you go down, and you have to get all sorts of craziness happening, which means that you don't have classical behavior.
Yeah. So points don't exist; they're not real, right? The idea of a point is an approximate
exactly.
thing,
Right.
and it has this fuzziness to it.
And then it's a question
Yeah.
of what the algebra is.
Yeah.
If you think of them as operators, because I think it's absolutely natural that one thinks of them as operators. I don't think you get around
Yeah.
without thinking of them as operators.
Yeah.
The question is, what is the hierarchy of
Yeah.
computation relations? Because presumably, what you wrote down may be the first part of the whole series.
Right. And so what you can do easily is to write the usual. We can write an x dot commutator that is consistent with this conjugate to the x.
Right.
And it turns out that that doesn't have any effect on. It's a negligible effect on anything you can observe. So it's only relevant if you go to the Planck scale, which is why I haven't included it in the story. But that dynamics exists in principle. And the other thing about that is it might not be an appropriate thing to do because this is only an effective macroscopic theory anyway. So by the time that becomes relevant, there might be a deeper theory, which is the correct way to look at it. So it's still a relatively superficial, effective treatment.
At some level must be related to
It's just very small.
momentum uncertainty.
And that's really very small.
And that contributes, but you're
It's
just
just saying
saying
it's very
you never
small.
get to those
That's right.
energies.
That's right. By the way, the equivalent velocity, it's kind of interesting, the regime of this experiment. So the frequency of the oscillation is megahertz frequency, but the velocity of the motion is about the same as continental drift, which is about 1 centimeter per year. That's how fast the mirrors move. It's ridiculous. That's what the technology can do. Yeah.
Well, let's continue
Yeah.
the conversation upstairs over coffee and cookies.
That's good. Thank you.